everyone, today we will discuss another soil chemical property which is the soil pH. Soil pH is the single most important chemical property of the soil. Knowing the pH will quickly allow you to determine if the soil is suitable for plant growth and what nutrients will be the most limiting. It refers to the negative log of the hydrogen ion concentration in the soil water solution. For these formulas, pH is equal to negative log of the hydrogen ion concentration, or it can be pH is equal to log 1 divided by the hydrogen ion concentration. The pH scale is how we measure the acidity or the alkalinity of the soils. At neutral pH, which is pH 7, the number of the hydrogen ions is just equal to the number and concentration of the if the hydrogen ion concentration is 0.000001 moles per liter, the pH of the soil will be 6. Using this formula. And at pH 6, there are 10 times more hydrogen ions than that at pH 7, and there are 100 times more hydrogen ions at pH 5 than at pH 7. Now let's discuss what's the relationship and what are the relationships between nutrient availability and plant growth with the soil pH. By the way, the most favorable soil pH for most agricultural crops is between 6 and 7, and the optimum value for soil pH is about 6.5. And the acidity and alkalinity of soils begins to be a problem for growing crops when it reaches the following: pH 5 and lower, pH 8 and higher. Strongly acid soils with a pH 4 to 5 can have high concentrations of soluble aluminum, iron, and manganese, which may be toxic to the growth of some plants. And under acidic conditions, phosphorus becomes unavailable for plant use when it becomes complex into insoluble forms with iron and aluminum as ferric hydroxyphosphate or aluminum hydroxyphosphate. If the soil is rich in manganese oxides, phosphate may also precipitate as insoluble manganese phosphate compounds. And other elements that may become unavailable to plants under acidic conditions are nitrogen, potassium, calcium, magnesium, sulfur, molybdenum, and boron. You see how nutrient availability is affected when a soil pH is acidic. The soil pH can also influence plant growth by its effect on microbial activity. The activity of bacteria is hindered in strong acid soil. At alkaline conditions or basic conditions, phosphate becomes complex with calcium to form the insoluble compounds such as calcium hydroxyapatite or calcium phosphate dihydrate. You can notice that in both acidic and basic conditions, phosphorus can become unavailable for plant uptake. Potassium may also be unavailable. When abundant, calcium competes with the potassium for absorption by plant roots. And also, most of the micronutrients become unavailable at high pH, except molybdenum. Iron deficiency commonly develops in alkaline soil. This is the soil pH scale, including the availability of those essential elements for plant growth. So the shaded area with color gray indicates the availability of those nutrients to the plants in different pH levels. For example, nitrogen is becomes limiting when The soil pH is lower than 5.5, and another example is that iron is becoming limiting starting pH greater than 7. So this that is how you can use this pH scale of soil pH relationship with nutrient availability. So there are different sources of acidity in soil. In fact, hydrogen and aluminum cations are responsible for soil acidity. Those elements are the major responsible elements making the soil acidic. Exchangeable hydrogen is the main source of each plus or hydrogen ion at pH 6 and above. Below pH 6, aluminum is the main source of hydrogen ions due to the dissociation of aluminum from clay minerals. Aluminum becomes more soluble at lower pH. This happens via this reaction. When aluminum is hydrolyzed, it is releasing additional hydrogen ions in the soil, making it more acidic. Now let's take a look on the different sources of acidity in soil. We have the first one, which is nitrification, that is the conversion of ammonium to nitrate. This happens when ammonium is oxidized from the use of common nitrogen fertilizers. This commonly happens with this formula. Ammonium, when exposed to oxygen, will be converted into nitrate, releasing, of course, also water and additional hydrogen ions in the soil. We also have organic matter decomposition. When organic acids ionize, it also releases hydrogen ions. We also have root respiration, as root respires when carbon dioxide and water um, reacts with each other, it will form carbonic acid, and when carbonic acid dissociates, it will also release hydrogen ions. Another source of acidity is acid rain. Acid rain is caused by the burning of fossil fuels. Burning oil, gas, and coal in power stations releases sulfuric dioxide into the atmosphere. Burning oil and gasoline in motor vehicles puts nitrogen oxides also in the atmosphere. And these gases, when mixed with water droplets in the atmosphere, can create weak solutions of nitric and sulfuric acids. And when precipitation occurs, the solutions fall as acid rain. Another source of acidity is the uptake of basic cations by plants. Basic cations are sources of hydroxyls to the salt solution. Examples of basic cations are these three: the calcium, magnesium, and potassium ions. These basic cations are taken up by plants, no longer contribute hydroxyl to the salt solution, therefore making the hydrogen ion concentration higher than the hydroxyl ion concentration. And because of that, hydrogen ions are being released to the salt solution. As the plant uptake the basic cations, can release root oxidates, also can release some of the hydrogen ions. We also have the leaching of basic cations as a source of acidity, because these basic cations are removed from the soil solution by leaching. They no longer contribute the hydroxyl ions to neutralize the ever-increasing amounts of hydrogen ions. For example, when calcium is exposed to water, it will combine, forming a new compound, releasing also additional hydrogen ions in the salt solution. We do have two kinds of acidity, what they call the active and the reserve acidity. When you say active acidity, it refers to the hydrogen ion concentration in soil water or moisture, and these hydrogen ions are in the soil solution. It is the easiest type of soil acidity to measure and has the most direct impact on plant health. When soil is simply referred to as being acid, it is usually the active acidity that is being referred to. When we talk about the reserve acidity, it refers to the hydrogen ions attached to the clay or organic matter in the soil particles and not dissolved in solution, meaning to say hydrogen ions that are adsorbed in the soil colloids. The term reserve derives from the fact that acidity associated with the exchange complex in effect can stand in reserve to combat against changes in the soil solution pH. And if acidity is removed from solution, for example, when you apply lime, the reserved acidity from the exchange complex can replace it, and the solution pH or the active acidity will not change appreciably. And because of that, we have what we call the buffering capacity of the soils. This is the ability of the soil to resist change in pH, either by acidifying or alkalisant agent. The amount of hydrogen ion in the soil solution is small compared with the hydrogen ion in aluminum ions adsorbed on the soil colloids, or what we call the reserve acidity. Neutralization of the solution hydrogen ion results in a rapid replacement of hydrogen ion from the exchangeable hydrogen ion on the soil colloid. Now, soils vary greatly in their buffering capacity. The greater the buffering capacity of an acid soil, the greater the amount of lime needed to neutralize the acidity. The higher the cation exchange capacity of a soil, the greater its buffering capacity. And soils with high CAC has more reserve acidity that must be neutralized to affect a given change in soil pH. Now, let me illustrate the buffering capacity of clayey and sandy soil. So this figure illustrates the buffering capacity of these two types of soil. Considering two coffee pots, we have the figure A, one 50-cup capacity and one 10 cups, both having the same size indicator tube and a spigot. Coffee in the indicator tube represents the active acidity, the one with you if you can notice the thin tube with an arrow labeled active acidity. Coffee indicator tube represents the active acidity, and that coffee in the pot represents the active acidity. The large pot represents a clay soil high in organic matter, while the small pot represents a sandy soil. Now, both pots have equal amounts of coffee in the indicator tube. They have labeled or leveled coffee in the indicator tube, meaning they both have same active hydrogen, so they have the same soil pH. Now, when you open the spigot, or the one that is the opening that can release the water by opening the spigot, or rather not water, the opening that can release the coffee, by opening the spigot and removing 1 cup of coffee from each pot. Please look at the figure B, indicating the release of coffee could be equated to the addition of small amount of limestone to an acid soil. So that is a method of liming. Now, opening the spigot will cause the level of coffee in the indicator tube to drop below the level in the pot, but will return to almost the original level when the spigot is closed, because some of the coffee from the pot will move to the indicator tube. The momentary drop of coffee in the indicator tube represents the initial increase in pH when you apply or added lime, and this affects the active hydrogen concentration on the salt solution or the active acidity. But reserved hydrogen soon equalizes the effect from the lime, and the pH returns to essentially its original level. So as you can see, that is in figure C. Thus, if the pH is 6.5 or lower, a buffer pH is run to measure the reserve acidity. The result of the buffer pH shows the amount of lime required to neutralize a major portion of the reserve acidity. Now, the relative amounts of coffee in 2 pots in figure C show why sandy soil and clay soil with the same pH results in different lime requirements make sense. Same pH level but different lime requirements because of different buffering capacity or different level of reserve acidity. For example, the small addition of limestone that is equivalent to the removing of 1 cup of coffee from each pot reduce the total coffee by 10% in the small pot, that is for the sandy soil, but only 2% of the large pot, that is for the clayey soil. In similar manner, a 1 ton of agricultural limestone will make a greater difference in the pH of a sandy soil than of a clay soil, because clay soil has high buffering capacity. Now, what is the importance of buffering? It tends to ensure reasonable stability in the soil pH and prevents drastic fluctuations that might be detrimental to plants and soil microorganisms. It also influences the amount of amendment, such as the lime or the sulfur, required to effect a desired change in soil pH. If you want to decrease the soil, if you want to increase the soil pH, you apply lime if it is acidic. If it is basic, you will apply sulfur. Now, soil pH can be buffered by the release of preserved acidity when calcium carbonate liming materials are added to the soil. For example, the active acidity or the soil pH is 6. You can also notice the soil solution having this cations, the sodium, potassium, the hydrogen ions, here in the first figure. Now, the active and the reserve acidity is at equilibrium in this stage. Now, when you apply calcium carbonate, this is the HCO3 minus, the carbonate ions consume the H plus or the hydrogen ions and create bicarbonate ions in solution, increasing the solution pH temporarily because the hydrogen ion concentrations decreases. But you can notice on the third figure for example, from pH 6, it becomes pH 7 because of the calcium carbonate addition, but it can return. It can be buffered by the release of reserve acidity. It could return to a pH of 6.2 because some of the hydrogen ions are displaced and transferred to the soil solution. Soil pH can also be buffered during soil acidification. For example, when to convert pH 6 to pH 4, it can immediately um, be pH 4 once you add an acid. But it can be buffered or can be returned into pH 5.5. This is the condition after some of the added hydrogen is adsorbed on exchange sites. pH rises to nearly the initial level. That can happen when the hydrogen ions coming from the acid you you added become become adsorbed to the exchange sites. Now, how can you adjust the soil pH? Since plants and soil organisms are adversely affected by extreme acidity that is below pH 5 and alkalinity that is greater than pH 8, soil pH must be adjusted so that it approaches the optimum value of 6.5. Acidic soils are easily reclaimed by adding lime, such as those materials having calcium and magnesium. The calcium and magnesium in lime replaces the hydrogen ion concentration or hydrogen ions present in the exchange sites. Now, how can you acidify alkaline soils? Number one, you can incorporate organic matter in the soil in large amounts because if you can remember, organic matter decomposition can acidify the soil. So therefore, you are decreasing the soil pH. Number two, addition of ferrous sulfate or sulfur mineral. Sulfur is transformed to a strong acid in in this case, sulfuric acid. Now, what is liming? When you say liming, lime is any material containing calcium and or magnesium, which when added to the soil can neutralize acidity. Now, the common agricultural lime materials are oxides, hydroxides, and carbonate of lime. So these are the common examples. For limestone, we have the calcitic, the calcium carbonate, and the dolomitic, which contains magnesium. We have the burnt lime, we have the slaked lime. Now, note that gypsum is not a liming material because the calcium in gypsum can displace the hydrogen ion in the clay particle, but hydrogen ion will remain in the soil solution and pH would not change because of the absence of carbonate. So it should have the presence of carbonate. Now, when we are adding liming material, you should be familiar with the relative neutralizing value. The RNV, or relative neutralizing value of lime, is its strength or effectiveness in correcting soil acidity compared to calcium carbonate. So calcium carbonate is our standard. RNV of lime is related to its calcium carbonate equivalent or CCE. The RNV of lime is computed from the ratio of the molecular weight of calcium carbonate and that of the lime mineral. So for example, if we are to compute the RNV of calcium oxide, we have this formula. RNV is equal to calcium carbonate divided by calcium oxide times 100. So in this calculation, you will have to know the atomic weight of each of the elements. So we have calcium, carbon, and oxygen. And atomic weight of calcium is 40, carbon is 12, oxygen is 16. Now just plug in the values of those, that is 40 plus 12 plus 16 times 3. Why is that 16 should be multiplied by 3? Because oxygen is what? Because oxygen has 3 molecules. And divided by 40 plus 16 for CaO times 100. You have the RNV of 179%. That is the relative neutralizing value of calcium oxide. When you say liming requirement, it is the amount of liming material needed to raise the pH of 1 hectare of soil up to a desired level under field conditions. For example, if it takes 2,000 kilograms of pure calcium oxide to neutralize the acidity of 1 hectare, how much of 80% of pure calcium oxide is needed to achieve the same effect? So to calculate for that, this is the method. That is only ratio and proportion. You just have to divide divide 2,000 kilograms with 80 times 100. So you will have 2,500 kilograms of 80% pure calcium oxide to neutralize the acidity of 1 hectare field. Now, let us discuss some of the beneficial effects of liming. Number one, it helps nutrients become available to plants because, as we discussed earlier, some of the nutrients or essential elements for plant growth are not available when the soil is acidic. It can also improve your soil structure. It can also provide nutrients for plant growth, such as an additional source of calcium and magnesium. It can also promote growth of beneficial microorganisms. So those microorganisms like or can thrive or live with a soil having a pH of 6.5. And it overcomes the acidifying effects of fertilizers, especially those ammonium-based fertilizers. Can also reduce metal toxicity to plants because some of the metals could be toxic to plants at lower pH level. Now, let's take a look on what they call saline and sodic soils. Saline or saline soils are soils having too high content of soluble salt. And this soluble salt, too high content of soluble salt can adversely affect um, plant growth because the increasing osmotic pressure of soil solution can restrict water uptake. As we all know, water is needed by the plants. And the electrical conductivity, EC, of the saturation extract is greater than 4 millimoles per centimeter. And the ESP or the exchangeable sodium percentage is less than 15. And the pH is usually less than 8.5. So meaning it is higher than 7 but less than a pH of 8.5. Now what is the difference between a saline and a sodic soil? Sodic soils, the ESP of sodic soil is that it is greater than 15%. Oh, that's the number one difference. Saline soils has an ESP of less than 15, while sodic soils has have an ESP of greater than 15. Its EC is also less than 4 millimoles per centimeter, and the pH value can range between 8.5 and 10. So it has a higher pH compared to saline soils. It is highly dispersed and poorly drained. It can have harmful effect on plants because of sodium ion toxicity and those that are associated with the hydroxyl ions. Now, how can we reclaim saline and sodic soils? Number one method, or the common method, is by flooding the soil. You can flood the soil with fresh water to leach out the soluble salts and sodium. That is if the soil is well drained. You could also create or build diversion canals to prevent entry of salt water. The sodium affected soils can also be reclaimed for agriculture by leaching. The sodium on the exchange complex must be replaced with calcium. So you can apply here gypsum. The calcium in the gypsum can replace the sodium on the soil exchange complex, forming the sodium sulfate, which can be leached from the root zone. So that's all for soil pH. I hope you learned from this video. Please don't forget to like and subscribe. Thank you.